Let's use the ladder operators to raise and lower the energy eigenvalues of the quantum harmonic oscillator Hamiltonian. First, I want to introduce something that's very important for the derivations that I'm going to do in this video. This is the commutation relation that links together A and A dagger. These collectively are known as the ladder operators. And this square bracket notation tells us that we're taking the commutator. And if we write the commutator out in full, we get this combination. First, we have A dagger, and then we subtract off A dagger A. And this is equivalent to 1. It's equivalent to acting with the identity operator. And I prove this in another video in the quantum mechanics playlist. This expression over here can be used to derive this expression. All we have to do is add this term to both sides. And that's equivalent to moving this term to the right-hand side. So that gives us this equation over here. A dagger is equal to A dagger A plus 1. So if we swap the order of these two operators, we have to add the commutator of the two operators. And this relationship over here can also be used to derive another alternative relationship. All we have to do is move this plus 1 to the other side, or subtract 1 from both sides. And that's going to give us this relationship. A dagger A is equal to A dagger minus 1. We're going to be using these two expressions in the derivations of this video. First, I want to write down the Hamiltonian for the quantum harmonic oscillator. So that is represented by a big capital H with a hat on top. And the hat tells us that we're dealing with operators. All of these operators have hats because hats in quantum mechanics denote operators. So let's have a look at H. H is equal to H bar omega times the number operator, it's a capital N with a hat, plus 1/2. Now this is the definition for the Hamiltonian of the quantum harmonic oscillator in terms of the number operator. And I've used this definition in previous videos. This number operator can be written as the product of the ladder operators, but it's a very specific ordering. So this is equivalent to H bar omega, this is just a numerical constant out the front, times A dagger A plus 1/2. So we have A dagger A. A dagger A is equivalent to N. And I'll make sure to put a little hat on top over here, because these guys are all operators. And the reason I am very meticulous about putting hats on top of all these operators is because I want to distinguish them very clearly from numerical constants. All of these guys out the front over here, H bar and omega, these guys are just constants out the front. These are the operators that we're dealing with. So here's what we've done over here. We've just written the number operator in terms of the ladder operators. We have A dagger and A. And the order is very important. A dagger and A, and then we have a plus sign over here. Now what I want to do is I want to use this relationship over here. I want to substitute this combination over here on the right-hand side in place of A dagger A. So that's going to give me the following relationship. We're still going to have H bar omega out the front, but now we're going to have A dagger A is going to turn into A dagger minus 1. But we still have that plus 1/2. So we still have plus 1/2. And if I combine this minus 1 and this plus 1/2 together, that's going to give me minus 1/2. And I'll write that over here. We have H bar omega, and then we have A dagger minus 1/2. So let's have a look at these two alternative forms. So this is the form that we started with. This is the definition that I've been using in the previous videos. I've expanded that definition in terms of the ladder operators. We have A dagger A in that specific order. And with this specific order, we have a plus sign over here. But now if we take this expression, which I derived from the commutation relation over here, what we get is a minus sign. So this minus 1 gets introduced. So A dagger minus 1 is equivalent to A dagger A. And this relationship over here allows us to combine minus 1/2 into minus 1/2. So when the order is swapped and the dagger comes second, we have to introduce a minus sign. So both of these are equivalent expressions for the Hamiltonian of the quantum harmonic oscillator. And they are, importantly, expressions written in terms of the ladder operators. Now we're going to see how we can raise and lower the energy eigenvalues using these relationships over here. So first, let's try and raise the energy eigenvalues. Let's try and do that. So what we need to do is we need to take the Hamiltonian operator and we have to apply it to a raised state. So a state that's been raised. And we have to use the raising operator. And a dagger is the raising operator. And we're going to apply a dagger to an eigenstate of the Hamiltonian. So this ket notation, this is just a state vector labeled by lowercase n. And this lowercase n is actually an eigenvalue of the number operator. It tells us the number of the state that we're dealing with. So inside the brackets over here, I have a state that's been raised. And then what we want to do is we want to act on this state with the Hamiltonian, and we want to see what eigenvalue we get. So we're going to end up deriving an eigenvalue equation involving the Hamiltonian. And first we're going to do this for the raising operator, and then we'll do that for the lowering operator. So now what I want to do is I want to take the definition of the Hamiltonian that's most convenient to use. And for this situation, this definition is most convenient. So I'm going to take this definition over here, and I'm going to apply it to this combination. So that's going to give me the following. I'm going to have h bar omega. Then I'll have this combination over here, a dagger a plus 1/2. And then that is going to be acting on this combination, and we'll have a dagger acting on the eigenstate. So can you see what I've done over here? I've just unpacked the Hamiltonian in a convenient form, and I'm acting on this raised state over here. So one alternative notation that you may find in some resources is a plus and a minus notation for the raising and lowering operators. So this a dagger is sometimes called a plus, and a by itself with no dagger is called a minus. So that's supposed to indicate that we're adding and subtracting the eigenvalues. We're adding 1, we're subtracting 1. So these guys come in different forms. You can have different notations, but they're all saying the same thing. These collectively are known as the ladder operators. Now, let's do some algebraic manipulation on this expression. I'm going to move this a dagger inside the brackets. From the right, I'm going to move it inside the brackets. So that's going to give me this combination. We're still going to have h bar omega out the front, but now I'm going to have a dagger a, and then I'll have another a dagger. So we're going to have a dagger a, and then a dagger. So it's a sandwich over here. A is sandwiched by 2 a daggers. And then we're going to have plus 1/2 times this a dagger. So we have this a dagger over here. And now we're going to act with all of this on the eigenstate. So that ket representation. This is the ket vector. And that is very useful in Dirac notation. So we're using Dirac notation because it's very convenient. So all I've done is I've moved this a dagger in from the right-hand side. And now what I'm going to do is I'm going to move it out on the left-hand side. And that's going to give me this. I'm going to move it out on the left-hand side. I'm going to factor it out. So I'm going to have a dagger on the outside, and then I'll put everything in brackets over here. I'm still going to have this h bar omega. I'll have h bar omega, and h bar omega is going to be multiplying a dagger, because I've gotten rid of this a dagger. So we'll have a dagger, and then we're going to have a plus 1/2, because I've moved this guy out. So we have plus 1/2. And all of this is acting on the eigenstate. So all I've done over here is, what's actually happened is the a dagger has come in from the right, and then it's knocked the other a dagger on the left. And then I've taken that a dagger out on the left. So I want you to make sure that this algebraic process makes sense to you. So now let's have a look at what we can do with this. This is not the Hamiltonian, right? This expression is not the Hamiltonian. We have a and a dagger in the wrong order, and we have a plus sign over here. If we want to make this the Hamiltonian, this has to be a minus sign. So what do we have to do? Well, we can swap the order over here, or we can make this a minus sign. Let's swap the order. Let's turn this into a dagger a. So we have to swap this around so we can get into this form of the Hamiltonian. We'll use this form of the Hamiltonian in the lowering operator case. So let's do this. I'll do this all the way down here. So what we have to do is we have to swap the order of these two guys. And we have to use this relationship. A dagger is going to become a dagger a plus 1. So let's substitute that in. So we're still going to have a dagger on the outside, but then inside all of these brackets, we're going to have h bar omega times, we'll have a dagger is going to turn into a dagger A, and then we're going to have to add 1. But what I'm going to do is I'm going to add 1/2 first, so we still have that 1/2, and then I'm going to factor this, this 1 out. So we're going to have plus 1 in here, but I'm actually going to factor it out. I'm going to take this h bar omega factor with it. So I'm going to have h bar omega over here. And all of this is acting on n. So have a look at what I've done. This is a very subtle step over here. So when I've swapped the order of these two guys, when I turned a dagger into a dagger A, I had to add to that plus 1. So I had to introduce this plus 1. So swapping these guys has added plus 1. And what I've done is I've moved that 1 outside of these brackets, and I had to multiply it by the factor h bar omega. So this has given me h bar omega over here. And importantly, this is plus h bar omega. And all of this is acting on the state. This is the eigenstate of the Hamiltonian. But have a look at this combination. Now that I've swapped this around, I have the correct form for the Hamiltonian. This is a dagger A plus 1/2. So I can write this as the Hamiltonian operator. So I'll write this as equal to, we still have a dagger at the front. All of this h bar omega stuff over here, this is going to turn into the Hamiltonian operator. So we have h with a hat. And then we're just going to have plus h bar omega. And that's going to act on the state. So this is a very important step now. We're going to take this combination and this combination we're going to act on with the state. And what is that actually going to give us? I'll write this out. I'll distribute all of these guys. And that's going to give me, I'm still going to have a dagger. I'm going to move this state inside. I'm going to act with the Hamiltonian operator. So the Hamiltonian operator is going to act on the state. And I'm also going to act with the state by multiplying with this numerical coefficient. This is h bar omega. So I have h bar omega acting on the state. So all I've done is I've moved that state inside the brackets. Have a look at this combination over here. If you remember the time-independent Schrödinger equation, that is actually the eigenvalue equation for the Hamiltonian operator. So if we act with the Hamiltonian on one of its eigenstates, that's going to give us back the eigenstate with the energy eigenvalue multiplying it. So this we can write as E sub n. That's the energy eigenvalue associated with the nth eigenstate. So that's going to give me this following combination. A dagger is still outside. It's wanting to get some attention, and it will in a moment. This is going to turn into E sub n acting on the eigenstate, right? That's from the eigenvalue equation for the Hamiltonian operator, which is also known as the time-independent Schrödinger equation. And then we have h bar omega also acting on n. I'll close the brackets over here. So that's h bar omega. This is a numerical constant. This is a numerical constant. We have an eigenvalue. And another thing, furthermore, this has to be a real value, right? This eigenvalue has to be real because the Hamiltonian operator is Hermitian. And Hermitian operators have real eigenvalues. So these guys are both real numbers that we can factor out. We can factor both of these guys out together. We can group them together, and that's going to give us this grouping. We're going to have E sub n plus h bar omega, and all of that is going to be multiplying this a dagger, right? We can swap the order because this is a constant. We're going to have a dagger, I'll put this in brackets, a dagger acting on the eigenstate. And have a look at this combination. A dagger acting on the eigenstate, we have that up here. And over here we have the Hamiltonian acting on this is the same as this constant multiplying this. So this is the eigenvalue of this state. And the eigenvalue has been raised by h bar omega. When we were doing this for number operators in the previous video in the quantum mechanics playlist, we had n plus 1 as a result when we raised the eigenvalue. But here we have the energy eigenvalue E sub n plus h bar omega. So we're not raising it by 1, we're raising it by h bar omega. H bar omega is the quanta of energy. So we have jumped up a unit of h bar omega. So this is a little chunk of energy. That is why we are dealing with quantum mechanics. We have quantized the system. So the energy only comes in discrete chunks. And that's what this raising operator has done. One important point I want to stress on is that I have commuted these constants with this operator. I'm allowed to do that because these are not operators. These are just numerical constants. So this eigenvalue can actually be swapped around. We can swap the order of these constants with this. We're not allowed to swap the order of operators in general because operators don't necessarily commute. Occasionally you get a special case where operators commute, but in general they don't. But you are allowed to swap these numerical constants. Now that's why I love to put these little hats on top, because that allows us to keep track of what we can swap and what we can't. So commutativity only works for these guys in general. It only works for these real numbers when we're multiplying them. And we can also swap the order of these two guys as well, because addition and multiplication is commutative for the real numbers. So we've done the derivation that I wanted to do for the raising operator. Now let's do it for the lowering operator. So we're going to have something of a similar form. We're going to have the Hamiltonian acting on a state that has been lowered. So we're just going to have A. So we're going to have A acting on this eigenstate. So that's very analogous to this form over here. Here we have A dagger, and here we have A. And we're going to write an eigenvalue equation that's analogous to this eigenvalue equation. So let's do that. But we're going to need a different form of the Hamiltonian. This form of the Hamiltonian is not going to be convenient with the plus sign. What we want is the Hamiltonian with this minus sign. So we're going to write the Hamiltonian with the order of these ladder operators swapped, and we need a minus sign over here when we swap the order of the ladder operators. So let's do that. Let's write this Hamiltonian operator as equal to h bar omega times a dagger minus 1/2. So that's what I'm going to write this Hamiltonian operator as. So this form of the Hamiltonian operator is far more useful for the derivation that I'm about to do. So all I've done is I've swapped the order of these guys and I've introduced a minus sign. And we know that's equivalent, and that follows from this commutation relation involving A and A dagger. So we have the Hamiltonian operator, and now let's have A and the eigenstate. So we still need A and the eigenstate. So this is analogous to this step over here, where we're just substituting a form of the Hamiltonian operator in terms of the ladder operators. Now, let's move this A in from the right-hand side. That's going to give us h bar omega times, I'll open these brackets up, we're going to have A dagger, A. So we have A dagger, A. Now we have a sandwich of A dagger. A dagger is sandwiched between two A's. That's the opposite of what we had up here. Over here we have a sandwich of A. A is in between two A daggers. So now these guys have swapped places. And what about this term over here? Now we're going to have minus 1/2 times A. So we have minus 1/2 times A. And all of this is still acting on the eigenstate, or this ket vector labeled by lowercase n. Now, let's do the following step. Let's move this from the left-hand side. Let's factor out A from the left-hand side. So it's come in, it's hit the Hamiltonian operator, and then it's caused another A to fly out on the left-hand side. So let's have a look. We have h bar omega still, but I'll put that inside the brackets. So we'll have A, and then we're going to have h bar omega multiplying. Here this A has disappeared, so we have A dagger A, and then we have a minus 1/2, and let's close all those brackets, and we act on the ket vector. So here we're acting on the ket. So have a look at what's happened over here. Now we have the correct order over here, but we don't have the correct sign. We have a minus sign. So over here we didn't have the right order, but we had a plus sign, but now we have the opposite problem. We have the right order of these ladder operators, but we have a minus sign, and this pesky minus sign is over here. So what do we have to do? Well, we can either change the minus sign or we can change the order. And it's a lot easier to change the order. Let's change the order of this combination of ladder operators. So we need to change A dagger A, and we have to swap those guys around. So A dagger A is the same as A dagger minus 1. And that's what we're going to do. We're going to use this substitution over here. We're going to substitute this inside. And that's exactly what we did over here. So I'll write that underneath. Here's what we have. We still have A out the front. So A is sitting out the front. H bar omega is still inside. Now, let's swap the order. Let's carefully swap the order. So A dagger A is going to get swapped to A dagger. So we're going to have A dagger. And then we still have this minus 1/2. I'm going to keep that minus 1/2 inside the brackets. But we're also going to have a minus 1. So when I swap A dagger A to A dagger, I have to introduce a minus 1. That comes from the commutation relation. So this minus 1, I'm going to factor out, and I'm going to multiply it by h bar omega. And now I have to multiply all of this. All of this has to act on the ket. So we're acting on this ket. Now we have an expression that is identical to the Hamiltonian. So this is equivalent to the Hamiltonian operator. We have h bar omega, that's this guy over here, and we have a dagger with a minus sign. So we have the minus sign and we have the correct order. So we know that this combination over here is equivalent to this combination. We have the correct order of a dagger, and we also have a minus sign. So let's write that inside. So we still have A outside. It's not getting in on the action, but it will soon. So we have A over here, and then we have the Hamiltonian operator, just a different form that we had up here, minus h bar omega. So now we're subtracting h bar omega. That's this minus sign over here. And all of this is acting on the eigenstate, or the ket, labeled by lowercase n. So we have an analogous combination to what we had over here. Over here we had the Hamiltonian written with the plus sign, and over here we had the Hamiltonian written with the minus sign. Both of these forms are equivalent to the Hamiltonian operator. But here we're adding h bar omega, and here we're subtracting h bar omega. Now let's distribute this ket vector inside. Let's multiply it inside. That's going to give us A, and then on the inside we're going to have the Hamiltonian acting on the ket minus h bar omega acting on the ket. And I'll close all these brackets over here. So let's see what's happening over here. We have the lowering operator acting on all of this combination over here. This combination together is the same as the combination that we see in the time-independent Schrodinger equation. So that's going to give us, I'll factor out the A, that's going to give us En, that's the energy eigenvalue associated with the nth state. That's multiplying the nth eigenstate, labeled by lowercase n. And then we have minus h bar omega. And we're also multiplying, we're acting on this ket with this numerical constant. So we're just multiplying, we're scaling it. And we're going to close all of this. So that's all inside the brackets. Now, let's have a look at what we can do with this. We can take all of these guys. These guys are both acting on the same ket. So we can group these guys together. They're just a numerical constant. And that numerical constant is going to be the eigenvalue of interest. It's going to be E sub n minus h bar omega. And all of that is going to be acting on the combination A, and then we have this ket. So this is the lowered version of the ket. So this lowered version of the ket is the same that we see up here. So we have A acting on the ket, A acting on the ket. And we're acting with the Hamiltonian operator, and that gives the eigenvalue E sub n minus h bar omega. So we've dropped down one of the quanta. So what is going on over here? So I'll write this out very explicitly in the bottom. What we have is that when the Hamiltonian operator acts on a state that has been raised, so when we have a dagger n, that is the same as raising the eigenvalue by h bar omega. So that's what we have over here. And I'll just write this explicitly. This is the relationship that we found from all of this blue working. And then we found another analogous relationship. So when the Hamiltonian operator acts on a state that has been lowered, have a look at what happens to the eigenvalue. Well, the eigenvalue gets dropped down by h bar omega. And this is a very, very important concept when we're trying to understand the quantum harmonic oscillator. So we have the Hamiltonian acting on both of these states. When it acts on the raised state, it gets an increase by h bar omega. And when it acts on the lowered state, it gets a decrease of h bar omega. So I'll draw a little diagram over here. So if we have the nth state over here, so this is the state n, and this over here is the state n plus 1, and this is the state n minus 1. The energy over here is going to be h bar omega larger. So if we go up, that's adding h bar omega. And if we go down, that's subtracting h bar omega. And how do we go up a state? Well, we apply the raising operator. We apply a dagger. So if we want to go up a state, we apply a dagger. And if we want to go down a state, then we just apply a. So a lowers the state and a dagger raises the state. And the energy gets lowered and raised by h bar omega. Now, h bar omega you can also write in terms of Planck's constant, not the reduced Planck's constant. Then you would have h nu. So that's just a way of moving the 2 pi's, the factors of 2 pi around. So h bar is actually h on 2 pi. And this omega also carries with it an implicit factor of 2 pi. And those 2 pi's can cancel, and that's going to give you h nu, or Planck's constant times the frequency. So this omega is the angular frequency of oscillation for the quantum harmonic oscillator. And these are the little chunks of energy that are associated with the quantum harmonic oscillator. So we've seen something very important in this video. We've seen how to use this commutation relation to write different forms of the Hamiltonian operator. All of these forms over here are equivalent forms of the Hamiltonian for the quantum harmonic oscillator. Then what we did is we saw what happens when you raise and lower a state. And that state is represented by this little ket vector in Dirac notation. So when you raise and lower those states, all you do to the energy eigenvalues is you increase or decrease by h bar omega. That is the quantum of energy. That's a little discrete chunk of energy that you're allowed to have. You can't have any energies that are in between. You can only have energies that are integer multiples of this. And you also have to add onto that the ground state energy. So the ground state energy is not 0. In fact, the ground state energy is 1/2 h bar omega, or h bar omega on 2. And you can see that from this expression over here. The ground state has to be 1/2 times h bar omega. So if this number operator turns to 0, if this is the ground state where n is equal to 0, the lowest possible value you can have is h bar omega on 2. And in the next video, we're actually going to find out what all of the energy eigenvalues are. We're going to find a general expression. So over here, we don't have a general expression yet. We just have the fact that we're raising and lowering by h bar omega. But what we're going to see is this is consistent with the eigenvalues of the Hamiltonian. In the next video, we're going to find the specific expressions for the eigenvalues of the Hamiltonian for the quantum harmonic oscillator. You can find all those videos in the quantum mechanics playlist if you click over here.